All right, guys,
Back to subject.
So, well, immediately start deriving something because it's like we can squeeze it in 5 minutes and then we can chat through it instead of doing long warm up.
Okay.
You know, last freaking part of chapter 4,
Burn bonds.
Oh,
Downtown. Gotcha.
yeah, without you.
Not, I was drinking.
No, I know, downtown on Sundays usually to eat like black coffee.
Get
and waffles.
pastries.
Yeah.
It's
Yeah, why not?
downtown on Sundays is really good.
Okay,
That too.
So it's on Friday, Saturdays really good.
you got like three files, right? In the email.
Yeah.
Okay. So what is given to Eva?
Where it's given to me. Back to the subject.
No.
Class may start.
That's good. That's good.
What else do I know? What other things do we say?
What do you remember of about 2-3 lectures ago? There was one picture, like fun picture, not scientific, that you were the only one who noticed.
The anchor?
Yes.
The cat and the castle?
Yeah. Just if everyone missed, just repeat what you saw.
There was a castle and someone was having an anchor, and I think they were trying to use the anchor to get up the castle like a hook.
Oh,
But that may be incorrect.
I do not remember.
I know there was something with the castle, but there's a castle in this. Yeah, see?
Oh.
So we're gonna see there's a tower,
Oh.
and you guys using the anchor to get up, anchor forward.
Okay, it didn't scare me.
So how do you interpret it? What is the relation between physical chemistry, anchors, and towers?
The ladder?
This is chemistry and what?
The ladder operator?
I don't know, this says it's
And
my
the
favorite
castle.
annihilation operator.
The
Coherent
ladder
states.
function.
So any other opinions?
It kind of looks like a Fourier
It's the
transform.
concept of a coherent state.
Yes, I like it better. But through the discussions, we can come to very wild and sometimes very correct ideas. So, no, I still need to give you a brief introduction. It just will not work without it. What did we do with this particle in the box? What were our advances? But when it
We
is,
talked about energy.
yes, but when particle is in the box, it's not a plane anymore. Later on we escalated to a 2- and 3-dimensional box, but if it is 1-dimensional, right?
Yeah.
Did we do anything time dependent?
Yeah, we did the.
Time dependent equation, which problem do you solve with this equation?
I don't remember.
Anyone remember? I'm trying to play.
What
drama.
problem the particle in the box did we use to time dependent Schrodinger?
Thank you.
I want to take a wild guess and say something along figuring out probability of where it is in the box. But
Yes.
so good.
F plus 1. So, do you remember what Tom worked? You will tell much better than I ever can.
Me?
Any of you.
About like figuring out using the TDSE where like in like the probability or like.
Yeah, what the solution look like? Just let's be simple guys, not equations.
I'm just, wait. What? I want to say it looked logically here. I want to say graphically that it was kind of like it was like a sinusoidal wave, I believe. Probably not, but Well, because it's a box. But I wanted to say as like time went on, your probability of it being within a box is going to decrease. So kind of like,
Okay.
I don't know.
No,
You get what I'm getting at, but I don't think I'm explaining it right. It's probably not.
One thing that they're telling me, it's main principle of computational chemistry. Which you can show.
At least I know the.
You're telling things correctly, so there was, something was oscillating, but do you have memories better than some?
Was this the sale function?
Huh?
Was this the sale function, the sales?
Sales went when we were considering density of states,
Oh.
and those are time independent. Those are just,
Right.
okay? It's a way to analyze eigenstates, but before time dependent problem, what did we do time dependent before the particle in the box?
The camel sign?
Was it the camel sign?
Yeah. So what about the camels?
They're pretty great.
Some, when one camel hump goes up, the other one goes down.
Perfect.
Yes.
And the center, if you take expectation value, which is you are a coach,
Yeah.
then expectation value moves forward and backward.
Yes.
It looks like a particle hits one wall, then another one, and just like and then bouncing forward,
Yeah.
right?
Okay, yeah.
Yeah, I know.
Expectation value of the position. So everyone remember this, right?
There it is.
Camels.
So
Camels.
can we let camels to practice harmonic oscillator? What camels will do this with oscillator? Huh?
Or not come out.
So if we set up the same problem in the harmonic oscillator, what are we going to get?
The same, the probability
Huh?
for. The same expectation value position for harmonic oscillator.
If we create initial distribution of probability of wave function inside the harmonic oscillator, if you will prepare literally above the equilibrium position and set zero momentum, it will not move. It will be an eigenstate. But if you take a ground state and elongate it, which means that we take this ball and a spring, what will happen?
Hang on, like that.
Right. Can you model it at quantum level? So
Yeah.
basically, it was Elsa did it,
Oh, Elsa did it?
but she
When?
was trying to squeeze it so quickly that we didn't focus because it was
Oh.
like last 10 seconds of
Yeah.
her talk. So we will create initial distribution, which is equivalent to ground state, elongate, and then release. And then our scientific question is, what would happen? We would analyze it in the same way as we did analyze the. I'm not meditating. I'm just trying to find the correct words. The Gaussian wave packet in the free space, or camels in the box.
Camels in the zoo, in their zoo enclosure.
So we need to answer the following questions. How the center, how the expectation value of the position would move, right?
Okay.
And what would happen to the uncertainty of the width of the wave packet? Okay. So when we were in the free space, the center was moving on a straight line, and width was increasing continuously as a quadratic, right? When we were in the box, we didn't care about width just because we didn't have time, but the central expectation value was oscillating, right? Working backwards. What do we expect to see for harmonic oscillator? What would happen to the expectation value of position? Just do what you did. So move forward and backward, right? Because you hit the walls. although walls are not walls, but like soft springs. Spring you exert return force and you go opposite. Like if it is a molecular bond, if you elongation and contraction of the good. What will happen to the beats? So we have several opportunities. It may increase infinitely, it may shrink infinitely, it may not change, and it may slow. Maybe something more. So I don't see it as a big scientific question, but it is a little connection that we can imagine, and we can apply a little bit more equations to satisfy curiosity if these questions create a maybe not. Maybe you're tired of the course and me.
No, we love it here.
Never.
Come again. Come
It's our
again.
favorite class.
Thank you. Oh. Oscillating, changing a bit. So there is tons of examples that you did in one of your previous homeworks. Like pendulum of you were doing some there were a lot of non-scientific examples,
Yeah.
but you know what you're talking about. So it is a question: if we use our everyday imagination, there is a instead of everyday imagination, there is a better word. Like when everything is good and following expectations, it is. You need to teach me the language. Common sense.
Oh, there we go.
Okay, so based on your common sense, the ball in a spring should oscillate, right? And shape of the ball doesn't change, right? And
not unless it hits a wall or something.
right, if it's like made of something soft, smashing, disintegrating. Okay, so it is an interesting exercise to see connection between classical mechanics, between common sense pendulum and quantized oscillator, and see if the conclusions will be similar. Right? So the concept of coherent state that we didn't touch yet, and we will start today, is an anchor to the tower, is tool that makes an opportunity to describe such oscillations in the quickest possible way from a mathematical point of view. If you do not have math of code and computers and you want to do it pen and paper. So I will ask you to, well, in the sense of the course, nothing should be trusted. You need to request proofs and I should provide them. But now I'm asking you to trust me for maybe 2 meetings and then I will provide proofs. So without providing proofs, we're just throwing an anchor to the tower and getting a new tool that we would allow to describe how things are oscillating in the oscillator, whether oscillator oscillates. Yes.
Something confuses me about particle in the box and harmonic oscillator expectation value, because the way I was looking at that, like the particle in the box, does it stop?
Oh.
And for the harmonic oscillator too, that doesn't stop. So like I think the particle in the box to oscillate in a way, does it not?
The question that Patricia is asking is very deep. I would say even too deep for our course. It is even a little too deep for the next part of your physical chemistry course. I will answer that. I'll try to spend not too much time. I wanted to derive first and speak second, but I failed. I want to point out several of you were doing errors, not in running codes or deriving questions, but describing them. And I do not want to announce, but I will secretly point on someone. If you the word equilibrium is absolutely unapplicable to this course. I know that when you speak about chemical reactions, you tell everything is equilibrium, Le Chatelier, blah, blah,
Yeah.
blah. Quantum mechanics is very non-equilibrium. On one hand, it makes it a little far from real life as a standalone course. On another, it makes it cool because non-equilibrium processes are much more complicated to discuss, to do experiment, and they're fun. Like non-equilibrium is when things are being blown up, exploded, right? So applying the word equilibrium to things that we are doing here is something I wouldn't do. It's not that it is, we never can merge together equilibrium process and quantum mechanics, but it's different world. Elsa? Okay?
Yes.
Non-equilibrium. When you say we solve non-equilibrium reactions, it will give you additional credit. Because equilibrium is boring, non-equilibrium is cool.
Okay.
The second part of physical chemistry will primarily focus on the equilibrium processes. Not that I want to say that it is boring, it is useful, but it will go over my head like 1,000 times. Instead of looking on one isolated model, like we are doing right now, it will make a summation over infinite number of replicas, like Avogadro number of molecules, ensembles. And then when ensemble is in equilibrium, one can find expectation values in statistical sense. And then they will be applicable to equilibrium. Here we work always with one isolated system, right? Isolated means it doesn't, the system is stupid. It doesn't know about the rest of the world. So it's either one electron or one harmonic oscillator in the whole universe, or it is just stupid harmonic oscillator that doesn't know that there are other oscillators around. And the concept of equilibration is very far from the tools that we are studying now. We do not neglect them, but like if you look on this little sandbox with all tools and operators that we play, they do not include tools and instruments to describe equilibrium. It will be different specialty. It will be like in addition to quantum mechanics, one needs statistics. Okay. What is the connection to the question of Patricia? If you want to make a little scandalous statement, then there is a big lie of quantum mechanics. When you were presenting postulates, and you are not responsible for this big lie because you just studied what is written in books. One of the postulates was that if one prepares quantum system in a specific state, it will stay there forever. Do you remember something like this? Like if your electronic quantum system is in certain eigenstate, it will be there forever. Right? If you do have superposition of a couple of eigenstates, the proportion of how the states are occupied will stay the same, and they may accumulate phase. So it will be some changes in time domain, but in energy domain, the distribution will not change. And this phase accumulation will be responsible for these oscillations and dynamical observations. But energy does not change. And what Patricia, so she just touched a question which is above this course and above next course. Why oscillations of this particle in a box or in oscillator, why they will stay forever, why they will never relax to the ground state?
Isn't it because they can't reach? I'm trying to remember. It's completely slipping my mind right now.
Maybe because you're oscillating.
The ground.
You understand what 0-point oscillations?
No, I was gonna say, well, can't the ground state only be as low as the total energy?
No, the key word is isolated. So in order to change energy of quantum system, we should break the isolation. We should break the ice and put it on a stove or put it in a fridge, right? And if it is isolated, it means it is inside a drawer and it doesn't exchange energy. Therefore, energy of the system doesn't change. and any oscillation will go on forever. It is an abstract concept. And then it makes this discipline that we're studying like self-contained and mathematically plausible. In order to get dissipation, one needs to practice next level. CHEM364 is offered in the spring, and you are strongly encouraged to take it because it is offered once in 6 years.
What?
Once in 6 years?
It's what offered once every 6 years?
Yes.
So, yeah, so like during your time out.
You have one opportunity to take it.
Yes.
Why is it only offered every 6 years? Like, it's kind of-
There is a
Is it class capacity? If you want to have
right.
students.
Even less than 5, they did it, and it's only like students who do computational theory needed, and typically it's 1 or 2 students per year, so I need to wait 5 years to accumulate it. Okay. I'm failing terribly. I thought I would derive something for 5 minutes and then chat, but I like chatting with you so much.
Derivation time.
Derivation time.
T over dx, there you go, we're done.
No, meeting is not done.
Close enough, close enough. So, no.
Oh, meeting. Right out.
Okay. So I just need to
She looked
focus.
over it right when she said that.
Nice. And it wasn't.
So, what is annihilation operator? Annihilation operator.
Annihilate.
Mhm.
That was one cute.
Factor.
Right? It goes from senior to junior,
Yes.
right?
Oh, yeah.
Is there something in front?
Yeah.
And then
N+1?
I think n-1 or simply n. So I do not trust my memory. We can check it later.
it should end minus.
So- I would probably would do just n. Now, how to express this operator in the Dirac notation?
What?
In Dirac notation, not direct, Dirac. Not Dirac delta, Dirac notation. Remember we were doing it. We were doing it in the like 2 lectures ago. So through cat and bra. So it acts. So bra and cat in the inverse order. Do you recognize?
Yes.
Okay, then square root of n, and then summation over all n, and this will be operator. It's kind of matrix notation that's written in the algebraic. Right? Now, here is a statement that I want you to believe.
Remember in the middle of the night?
It is.
No. It will be unfair and too much to ask from you.
Oh, okay.
Dimitri, the right-hand side is supposed to be n+1. Under the square root.
He's unsure about that.
The junior and senior.
Sure?
Yeah.
No.
Oh.
This I know for sure.
Respectfully.
If it would be a little dagger, a little cluster, yes.
Which just N.
Yes.
Alright.
Okay. So the goal is to look how oscillator oscillates. And I ask you to trust me that the concept of coherent states will help to solve this question. Now, do you think that you need to do it, or you try to do it for a couple, and then I will provide proofs. So if we find an eigenstate of the annihilation oscillator, then this state will be very helpful in describing oscillation. And the name of the state is coherent state. So typically, we find eigenstates of Hamiltonian. Some crazy people find eigenstates of momentum operator. Later on in the class, you see that some people find eigenstates of the angular momentum rotation operator. But now we need to look for eigenstates of the annihilation operator. How do we go forward? We assume that this state, unknown state psi, we can put index alpha because it will be eigenstate and index. So it is expressed as a superposition of eigenstate of harmonic oscillator, right? And we do need to find this coefficient C sub n. Right? So if we do have this equation, and this equation, we just need to combine them together. So we plug this one into there, and this one into here, and into there. Okay?
Okay.
I'm not telling that we are done, but basically the conceptual part is done. The rest are math and analysis. Science should be done in color.
Sorry, the K you changed, does this still mean,
Mute index. The index that will disappear when we practice chronic delta. So I'm going to rewrite this equation. So summation over k square root of k minus 1 get k bra, then summation over m c sub m equals eigenvalue summation over m c m. So on the right side, we will not change anything, but on the left side, we should see that bra and ket meet each other ecstatically, and the expression can be simplified, right? So first, I'm going to summation and expansion coefficient can be safely moved outside, because we are forbidden to swap orders of matrices and vectors, but constants and summation signs, it doesn't matter what it is. So summation k summation m c sub m square root of k ket k plus 1, and then k
Is it K minus 1?
minus 1. Thank you so much.
+1.
Yes. Plus 2, it's important. They will screw up next 2 weeks. If-
+1 value.
So, when you see this bra times ket, what does it mean?
Delta.
Delta.
Yes. So delta sub kn, which means it is 1 when they coincide and 0 when they don't. So out of this, do something like there are summations over 2 indices, right?
Yeah.
And the object here has also 2 indices, it's like matrix. And when we apply it to matrix, it means we just pick a like row or column, convert matrix into that. So I'm skipping this one yet and just continuing from here. So when we have this delta Kn. We have a snake and a rabbit. And as for rabbit, but as a result, both disappear, right? So this one disappears, and one of the summation signs disappears.
Does it matter which one disappears, the K or the M?
Just do it consistent. So if I decide to remove summation over n, it means everywhere where I saw index n, I will replace it with k. Right?
So summation C sub K.
So then you have summation over k, p sub k, square root of k, k minus 1. Much simpler. Not a done deal yet. There is a trick. We are going to establish equality between left and right sides. And we do have, like here we have basic states n, and here n k minus 1. And we need to establish equality. So if you want to do so, can we replace, can we do another substitution? So we will just replace k minus 1 will be replaced by n again. So k minus 1 equals n, then k equals n plus 1. And everywhere where we have k, we will put n plus 1. So it will be summation over n, c n plus 1, square root n plus 1, n.
I have a quick question.
Yes, yes.
So on the left hand and the right side, like before we canceled out the n's and swapped them for k's, that was a different index than what was already on the right hand side of the equation.
The namings of the indices, I wouldn't say it is a mystery for me, but I'm very sloppy about it. Before we make two things equal to each other, it doesn't matter the name of the index, because it's just when you do integration, the variable disappears when you do integral, especially the finite definite integral. The variable of integration disappears, and no one cares what was named for this variable. The same for index. So index in summation is something we integrate over. Yes, please.
Or we also have delta Kn.
I'm just going to focus you in case you say something more.
Great. For we to have delta Kn to be equals to 1, that means your K equals to 10, right? Well, for we
Just guide me. Should I speak about this or the?
yeah, I want to. What I'm asking is, for this to be equal to 1, for us to cancel out for it to be equal to 1, this equals to this.
Yes.
So if this equals to this, then why do we have this?
Oh, this is different thing. Absolutely different thing. We can I can confuse you but make it more logical. What if we use letter M here?
Okay, make it out.
Okay. And then we replace K not to N but to M. M. So they are different things. Is it better?
Yes.
Less confusing?
Yeah.
So now we need to establish equality between these two things. So I'm not going to do anything new. I will just rewrite what we already got. summation M C M equals summation M C M plus 1 square root M plus 1.
Don't have that alpha somewhere. Wait, I thought it's on the other side.
So acting by initiation operator to the wave function provides the same wave function multiplied by eigenvalue.
It should be on the,
Oh, wait,
on the left.
okay. M plus 4.
I'm racking up the points today.
Okay, now if we do have two series, right, and we know that they're equal, what is the mathematical condition for them to be equal? In which case, these things will be equal.
Alpha equals square root of M plus 1. Is it?
Let's describe it more generally. Like if it is not this one but any, for example, if we have summation of a n x x n equals summation of b n x n. Like if you get x sub n will be our basis superscript and your basis functions, in which case this summation will be equal.
Next is there.
Huh?
Next is question zero.
No, we want it to be correct for any x.
A sub n equals B sub n.
Yes. A sub n equals b sub n for any n. Now let's it's too mathematical. Let's speak about it in more human language. So expansion coefficients in front of equal powers must be equal. Okay, you all good?
If they are equal, why do we have to represent them as different?
What?
Like, if they are equal, why do we have to represent them with different variables?
It could be something more complicated, not just it's a function of m. I'm just generally introducing it. So as soon as you believe this little statement, I'm going to erase it because it uses our precious space. So coefficients in front of the same powers or the same base functions must be equal. So then, by saying this, we do not need summation anymore. We do have the alpha c sub m equals c sub m plus 1 square root m plus 1. So what do you think of this expression? Do you like it? Maybe you don't like it.
I think it makes sense.
So can you speak more about it? Something in addition that you like it. What else?
I don't know, maybe if, to me, it would make sense if it was not C subscript M, maybe it was C subscript another thing. Another letter, it would make more sense to me.
Only for Patricia. Let's replace it to letter.
Maybe two sides, like just for like, like here is no hand, and it's A, and that is M, and it will make more sense. Do you understand?
No. I think with Patricia we found each other. She doesn't understand what I speak. I don't understand what she speaks.
There are
It's a great thing.
yeah, if you just say this are equal, maybe if this subscript is A, And this equals this. So saying this equals to CM plus 1. I don't know, I just find it weird. I don't know.
Wait, stay here, stay here, stay here. We didn't focus camera in the right way. Just repeat what you do not like.
Okay, I understand if this subscript is another a letter,
Mhm.
if it's another letter, it would make more sense to me when you compare that this is because to that. If you compare.
Okay.
But because you said M equals to CM plus 1, it's just like we,
Paradoxic.
yes.
Okay, yes, yeah, thank you. I really wanted someone to say, I just didn't recognize the way how Patricia expressed it. So we do have connection, well, it's not equal, it's something coefficients, connection between like junior and senior of the same sequence, right? So if we know something about junior, we can find something about senior. The element is related to its predecessor, right? So any smart mathematical words for this?
Or what about it?
And minus 1 on this one.
Yeah.
Yeah.
Did you hear it before?
Recursive formula.
Yeah.
What? What is that?
Bro, what's the plus 1?
None of you guys think algebra.
Recursive means like going backward.
Yeah,
So
because it doesn't it mean that, or yeah, it just means that it's the opposite of something else,
so
or like the
let's say
backwards version of something, right?
M plus 1 is equal C sub M multiplied by alpha divided by M plus 1, right?
Yes.
Okay. So suppose we do know C
Oh, yeah.
naught, right? Now, how can we express C1? C1 will be equals alpha divided by square root of 0 plus 1 times C naught, which will be alpha C naught. Right? No, C2 will be alpha divided by square root of what? No, it's the same here and there. 2
2 plus 1.
times, no, it's M, if M equals 1, you see, we are going from this to this.
Okay, okay.
To square root of 2, C1, and then we can plug C1 from here, right? So it will be alpha square root of 2, alpha C naught. Okay, let's keep going. C3. So it's alpha over square root of 3 times C2. But C2 can be taken from here. So alpha square root of 3, alpha square root of 2, alpha square root of 1, C naught. Can you say what will be the element number n? Or m, if you like these letters. C sum m equals
Alpha
alpha to the power
to the M.
m divided by
N minus 1.
Wouldn't it be like a factorial?
yes, just m factorial.
N factorial.
You know. Okay, and in order to find any element, we need just to define what is alpha and what is C naught. Okay, I think it's still I still have a lot of failures this time because I even didn't start it showing slides. Whew. But here is what we did, right? And okay, maybe it will be the last slide because time is really up. Yes. Here is, I'm showing to myself, but not to you guys. So here is the plan. What we need to solve the prediction of future for non-equivalent state of the harmonic oscillator, which means expansion coefficients will accumulate the phase, right? And then we can find any observations, including how it will oscillate forwards and backwards and many other things. But these expansion coefficients will be taken from what we already did. And we need to multiply it by phase accumulation factor. With this, I would like to give words to Eva. And let's announce.
Meeting is done.
Meeting is done. Yeah.
Oh my God.